Officially welcome everyone to our presentation today, along with our friends at Edge Impulse. We're really excited about this one. The topic today is Smart Vision, Smarter Industry, which really is just a fancy way for us to talk about implementing vision-based edge AI solutions, really in legacy industrial environments, which actually, now that I say that out loud, still sounds pretty fancy. But today, at the very least, I hope we can inspire you to envision how you might start thinking about modernizing maybe your existing practices through this, what I think is a pretty magical combination of Edge Impulse and Blues. So what we demonstrate today is going to start with the Edge AI platform you all know and love, that being Edge Impulse, or if you don't already know and love them, you will after today. We'll be using Blues for the secure wireless connectivity and its turnkey cloud integration capabilities with AWS, Twilio, and SendGrid. Now, this here probably looks a little complicated. We've got 5 distinct services, but the beauty that I think you'll see today is how simple these all are to orchestrate together. Well, AWS, okay, AWS is kind of crazy in and of itself, but I do stand behind the fact that there's a lot of complexity that is handled by the services we show you today, and we're going to somehow tackle all of this in less than an hour. Before we really start, if you have any questions that pop up during the presentation today, go ahead and ask those using the Q&A panel provided in your Zoom UI. We're going to actively answer as many questions as we can while speakers are speaking. And if we have time at the end, we'll do more of a public Q&A with some of the best questions. Of course, question we always get is this being recorded? The answer is, of course, yes, it's being recorded. It'll be available here on the Blues YouTube channel at this URL. While you're there, I'm always going to recommend you subscribe so you're the first to learn about all of our fantastic video and webinar content. So with that, let's do some quick intros of our speakers, and we're going to start with David Tischler, who's a program manager at Edge Impulse. Hello, David. From
Hello,
Edge Impulse.
everyone.
Sorry. We also have Owen Jordan from Edge Impulse. Owen's a developer advocate there. Thanks
Hello.
both of you for joining us here today. We also have TJ Van Tolles, a principal developer advocate here at Blues, and I'm also from Blues. My name is Rob Lauer. Really good crew here today. This will be a good one. So I wanted to kick off our conversation today by answering a question. And to me, it's always one thing to present a solution to you all, but it's another to present that solution without framing the real world problem that we're solving. And so my answer to this question today is that really integrating these modern vision-based ML solutions into legacy environments can be a massive challenge. What makes it a challenge? Well, frankly, like complexity in the model development itself. It's not that easy to create valid, robust ML models for legacy systems, right? We're going to kind of address this by showcasing how Edge Impulse and Edge Impulse Studio really simplify model creation for numerous scenarios, not even just the ones that we're talking about today. Hardware limitations. So when you're retrofitting legacy solutions with vision-based ML, that's going to demand scalable hardware solutions. You can't void the warranty. You need to be external to the product generally as well. So we're going to demonstrate how to deploy ML models on a Raspberry Pi for prototyping with pathways to more industrial scale options like the Jetson Orin Nano, for instance. And we're going to do it all separate from the system itself. Connectivity constraints. So many industrial environments, they usually rely on traditional IT networks, Wi-Fi, Ethernet, and they may be restrictive. For example, local IT often doesn't want to provision Wi-Fi access on their network for security reasons. So we're going to solve this by using the Blues Notecard for secure real-time data syncing via cellular, eliminating local IT network restrictions. Also, this is important too, vision-based ML applications, they generally need significant data throughput if you're relaying those vision-based inferences, like literally images or video to the cloud. And so today we're going to introduce a new Notecard cellular option that offers higher bandwidth capabilities at a lower cost. So to translate all those problems and solutions explicitly into what we're showcasing today, um, this is wrong. I just learned. We're going to be showing off what I'm terming a multi-model Python solution that implements both an object detection
Wait,
model and an anomaly detection model in the same application. I say this is wrong because it's not technically a multi-model solution.
wait, Rob, let me jump in here. It is a multi-model solution. it's not a multi-impulse compressed and binary
Okay.
built into one singular deployable EIM file. But this is
Yeah.
correct. It
Okay.
is a
Okay. All right. All
multi-model
right. I
vision
take that
based.
back.
Yeah, yes, it
All right.
is.
Thank you,
It's
David.
all about the terminology.
That's right.
Yeah,
Uh,
yeah, the multi-impulse is one EIM, but yeah, we
Yeah,
were
yeah.
we'll
we
get
were debating about that before
we'll
the
get
call,
into
but yeah,
that.
sorry.
You're good.
As just mentioned before, too, the Blues Notecard is going to bring us an easy way to provide secure, literally off the internet cellular connectivity. And then in turn, using AWS along with Twilio for SMS and SendGrid for email, it's going to give us that real time or near real time alerts when anomalies are detected. Again, sounds like a lot, but we're going to make this look easy, I promise. So, with that, I think I'm going to turn things over to David for a quick primer on Edge Impulse.
Right, thanks. Now I just have to figure out how to share. What are we in today? Zoom? All right. Let's grab this over here and I'll start us off. Can you see that?
Yeah, looks good.
All right, excellent. Thanks, thanks. Those of you who have seen our webinars in the past have probably already a pretty good, solid experience and understanding of what Edge Impulse is. But Edge Impulse is a platform that allow you to build custom machine learning models. Okay, and what I mean by custom is this. There are many existing ML projects and ML models already out there in the world. If you want to detect a banana, I guarantee that there are plenty of existing ML models that turnkey can tell you, well, that is a banana, whether it's through image classification or object detection. Those types of problems have already been solved. But, in the context of industrial, right? Let's say you are in the business of manufacturing valves like this. Is there a model right now in the world that can tell me precisely what type, make, model, and if this is a good valve already that I can just download and go? Not really. So what you need to do when you're looking to build a custom machine learning model is collect your data, build your algorithm, and then deploy that onto an edge device. And we're talking about anomaly detection today. So in sort of a manufacturing context, maybe another example is, how about if you are, I won't name any names, but a large toy manufacturer that makes a very popular doll by the name of Barbie. If you are in the business of building flight attendant Barbie and you know what a proper flight attendant Barbie should look like, well, then what you want to do is collect images of that proper, perfect, pristine flight attendant Barbie and build a model that can identify and recognize any defects as they come down the production line. So that's what we're going to showcase today. And minus the Barbie, we're going to use some bricks. Let's go on to the next one. The workflow, as I've started to describe here, is pretty simple. Data collection. Any machine learning project is going to require your custom data set. So data collection is where we'll begin the process. We'll go through the building of the model, the building of the model being the impulse or the pipeline. Then train the algorithm. There's some optimization and testing that can occur. And then you deploy that model to the edge devices. And of course, in a good ML ops loop, you want to also ensure that your model is functioning well, high performing, and bring back more data from the field where the model was actually deployed. And that's what Blues will allow you to do. So Rob and TJ will cover that a bit more in detail later on. Once you have more data, you start the process all over. Add that new collected data into your data set and retrain your model and start the loop all over. So benefits of Edge AI. The reason that we're talking about doing this at the edge, we've been through this before in the past, but some of the good talking points here are around privacy, data stays on the device. In the case of bringing more, well, I should say the inference results are done on the device, not in the cloud. In the case of bringing data back, well, then of course you're going to transit the network, but the inferencing is done locally. There's no need to send the frame that you want to inference up to the cloud to then be inferenced there. Low power, the bandwidth and latency, of course, by the fact that the algorithm is running on the edge device. And costs, save on storage compute costs by not sending the raw data constantly to the cloud. And you're doing your data set augmentation. That's a different story, but at least you're not inferencing all day long across the network. So we kind of touched on this one already as well. We're mostly focused on industrial and digital health. There are a few other types of products, industry verticals that we've helped out with as well. But primarily, we focus on the manufacturing industries, transportation, commercial applications. And then over in the health world, you see a lot of biosensing, things like PPG, EEG, classification and detection for gesture recognition. So there's fall detection. In the audio world, you've got audio classification and keyword spotting. So you can, listen for sounds in the environment, things like that. Today, of course, we'll show off industrial, so you get a better sense there, but production quality and optimization, and that could cover vision, that could cover audio, that could cover sensors. Some of the use cases we see here when you're talking about image or vibration or sound, temperature and current, of course, your machine health, predictive maintenance, HVAC systems. If you think about commercial offices, commercial real estate, the HVAC is up on the roof. If for a very simple example, if you're able to hear that a compressor is not sounding the way that it normally sounds because you happen to be in close proximity to it, well, that's fine. You can then have someone investigate that to make sure that, the compressor's not out of balance or, about to fail. You have somebody take a look at it. But when these machines and these systems are not within earshot, that's when sensors and microphones can stand in and alert for predictive maintenance use cases. So visually anomaly detection is what we're going to show off today. I'm probably going to let Owen speak more to this, but as you can see in the screenshot here, what we're going to do is take images of known good bricks that Rob's got, and then we're going to look for defects. And the algorithm is going to identify the defects visually by overlaying onto the image a heat map. And that heat map is essentially the anomaly score. Like you can see in the slide here, the max, the mean, and we're going to do a numerical confidence or deviation from norm. And that's going to indicate where a defect on an object is located. And I suppose the slide is a little bit more of the same, but because the algorithm, because the model is running on the edge device, that can be done across an MCU, a CPU, or a GPU, or in some cases, devices will even have an NPU. And it's done in real time. And kind of like I was talking about in that use case earlier, we'll show how an alert can be sent, an engineer can investigate, and a fix is deployed. So Rob, you're going to be alerted and the engineer and deploy the fix today. And for HD Visual AD, this is actually one of our newer ones where using patch core, oh, and I'll let you cover this in a bit, but using patch core, we get a higher resolution capability for the anomaly or the defect area. We did cover the hardware targets already, but these models can be deployed to MCU, CPU, GPU, or NPU. We're going to show CPU and talk about GPU today, but MCU and NPU are also fair game. That's it for me. So I'll turn it over to, is it TJ who's taking on?
Yeah.
All right.
When you take your screen down, I'll bring mine up.
Here we
And
go.
basically what I want to do is give a quick primer on Blues, much like David just gave a quick primer on Edge Impulse. And essentially what I want to do is give you enough context so that you can follow along with the demo that Rob is going to be showing off here in a minute, at least the connectivity part of things. So at Blues, we are known for Notecard. I've got one here. It's about a 30 by 42 millimeter connectivity module. And what Notecard allows you to do is add cloud connectivity to your physical products. So we occupy this sort of middle space between the product, the thing that you actually pretty much want to be working on, and focus on the unique thing that your product does, as well as your cloud applications, and let us enable the data flow between the two. And in an industrial setting like we're talking about today, this can often be fairly messy because in this sort of setting, sometimes there might be a Wi-Fi network, but sometimes those Wi-Fi networks can be hard to access or use. Or you might be working on some critical infrastructure where you have to know that you get alerts or warnings out regardless of the Wi-Fi state, like say the power goes out or something like that, and you need to send something out. The Notecard can be really advantageous in those situations for enabling connectivity. So what gets people excited about the Notecard? Well, our cellular Notecard is available in 140 plus countries. We have connectivity in a lot of areas worldwide. The Notecard comes with 500 megs of data and 10 years of service included with the cost of the device. You can configure a Notecard with just 2 lines of JSON that I'll show here in a minute. That's really as simple as it gets for connecting your product to the internet. And Notecard is very low power friendly as well. So it consumes only 8 to 12 microamps while idle. So it enables a lot of low power scenarios that would otherwise be very difficult or impossible to build on your own. There are multiple different types of Notecard. So we have cellular, Wi-Fi, LoRa, Cell plus Wi-Fi, and a satellite module that we call StarNote. But you'll notice that all these Notecards share the same form factor. They have the same M.2 edge connector on them, which allows you to build hardware where you can quite literally swap between different Notecards and swap between different radio access technologies. And these Notecards also share the same API as well. So not only can you build firmware that is Notecard agnostic, so radio access technology agnostic, but you can also build firmware that works in that same way as well and operate in a way that is totally abstracted from the radio access technology that you're using. So it looks something like this. I mentioned earlier, you only need 2 lines of JSON to connect a product. These are those 2 lines. The first is a request we call hub.set. This passes a reference to a product that you set up in our cloud service that we'll look at momentarily. And then the second request is a note.add request where you just actually work with data. So this would be an example of something working with temperature data, but this could contain arbitrarily any data that you want. In Rob's example in a minute, he is going to be using some image data as part of the notes that he will be sending. And all you need to do is be able to send the Notecard this data over UART or I2C. So that's something you can do from virtually any host microcontroller, any single board computer. And to make it even easier, we provide a handful of SDKs for popular platforms that you can use for interfacing with a Notecard. So Rob will be showing off our Python library, which we call NotePython. But the steps that Rob is taking are something that you could also do in Arduino, in C, in Go, in Zephyr, and pretty much any language or RTOS out there. You can communicate with a Notecard pretty simply. We oftentimes call the Notecard a device-to-cloud data pump, and that's because Notecard knows how to securely talk to its backing cloud service, NoteHub, out of the box. So NoteHub is a secure cloud proxy for Notecards. And from NoteHub, you can then route your data to any cloud app of your choice. Basically, how it works is the Notecard, when you get it, you just run those 2 lines of JSON on it. You tell it about your project in NoteHub, and your setup at that point is complete. You essentially have data flow unlocked. And then once your data goes into NoteHub, it is basically you have NoteHub acts as sort of a mission control from there. So you can use our API to pluck your data out. You can route your data as it comes in. So you can say, in Rob's example, he's going to say, as data hits NoteHub, immediately route it to AWS so I could take further action. You could send it to dashboarding platforms. You can send alerts. There's a number of things that you can do that NoteHub unlocks once you have data flowing into it. You can manage fleets of devices. So NoteHub will also help you as your project starts to scale. So you can manage different fleets of devices. You can also do firmware updates in NoteHub. So a lot of these features, as your project starts to grow, you start to need to work with dozens or hundreds of devices. NoteHub can help you do that as well, and all in a very secure way. I think the easiest way to see the value that Blues is providing overall is to talk about the things that you don't need if you choose to use Blues for connectivity. So with Blues for cellular, you do not need to bring your own SIM or separate mobile plan. The note card has an eSIM built into it. The data is included with the cost of the device. You don't need to interact with the radio directly. So again, everything is done through that JSON API. So in the case of cellular, that means no talking to a cellular modem using things like AT commands. Similar story for satellite, for LoRa, for Wi-Fi as well. We abstract all of that behind a JSON API. You don't need to bring your own security implementation. Again, you don't need to do your own firmware updates. Firmware updates are becoming kind of a thing you must provide in certain jurisdictions. NoteHub and Notecard can help enable that. Power management is a lot easier. Custom cloud integrations. Again, sending data to AWS from an edge device is not always the simplest thing, and we make it really easy through our process. And then also certifications. So all note cards are also FCC and PTCRB and product certified as well. Now, finally, I like to end with this chart because this just sort of lays out the whole picture of what it looks like when you choose to use Blues for connectivity in your product. Everything still starts with your hardware. So you bring your microcontroller or your single board computer, your sensors. So in the case of Rob's demo, he's going to start with a Raspberry Pi running our NotePython SDK and a camera attached to it. He'll use that same SDK to format that data up into the JSON that the note card expects. She'll queue that data on note card, and then at an interval you specify, note card will securely synchronize that data with our cloud backend service, NoteHub. And then again, from NoteHub, you're sort of in control of your data. You can send your data wherever you want. When it comes in to multiple different places, to one place, whatever makes sense. So Rob will be sending the data to AWS so that he can send out some text messages. And then finally, you can send this data in the opposite direction as well. So you can also start in the cloud and say that send data all the way back down to your device. This enables a lot of sort of smart device types of things. So if you have a piece of industrial equipment that you want to remotely turn off or change some settings on it, that's something that we enable. This is also the process that makes our firmware updates possible because we need to be able to send information back down to a device, and we do so through this mechanism as well. So that's the overall picture of how Blues works. If you have any questions about getting into more specifics, just let us know in the comments. We'll be happy to help you out. But one last thing, because Rob did mention, and if you read the description for this webinar closely, that we would be talking about a new note card. So Rob will be showing off one of our new mid-band note cards. So these are note cards that we announced sometime last year, but it is now currently in beta. So we now have the things. And so I'm holding one right here. Rob's got one. Some of our users and customers are trying them out. These are note cards that use the LTE Cat 1 Biz protocol. This is a single antenna variant of LTE Cat 1. And because it has a simpler design, it is a note card that we can offer for cheaper, and it's more compact than our wideband note cards, while still offering plenty of connectivity for the types of projects that our users are building. And speaking of those projects, Rob, at this point, I'm going to send things back to you.
Yay.
Because we've done enough talking. We want to see this thing in action.
We need to see the demo. Yeah, the other thing about the LT Cat 1 Biz that's kind of interesting is with, I believe it's AT&T that's dropping support for NB-IoT as well. So we're starting to see, like, as there are higher bandwidth protocols available globally, that we're going to see that continue to happen, I think. And actually, LT Cat 1 Biz is available anywhere LT Cat 1 is already available. So it's not anything you need to worry about in terms of availability. So, all right, it's demo time. However, let me share this.
Dramatic pause. I love it.
I say, however,
Yeah. I'm on the
because
edge of my seat.
um, I do have the privilege of showing you all off this miniaturized industrial conveyor belt that's to my right here with Raspberry Pi 5 with these awesome Blues branded bricks that I think you can kind of see. It's like my favorite thing I bought in the last year. So these are all going to represent this like fictional company we can say that I started that's focused on manufacturing these bricks. But in case my live demo fails, which is entirely possible because I have cats and everything's kind of carefully orchestrated over here, I do want to kind of walk through the process really quickly in slide form. Um, and for me, step zero was to really identify the problem, and that being again this fictionalized company that manufactures bricks. These bricks roll down the assembly line or the conveyor belt here. They roll down at a pretty fast pace, and we obviously would like to identify defects in the bricks before they're packaged up. So using an automated system like this, of course, it's going to help me increase the speed at which we can inspect products. It's going to improve overall product quality. And it doesn't take much of an imagination to think about how you can apply this concept of both object and anomaly detection to many, many different scenarios. That's why I'm extra excited about this demo today. Step one for me, I need to be able to detect bricks on the belt. And to do that, I need to build an object detection model using the cloud tooling, the web-based tooling provided by Edge Impulse Studio. So to build that model, I need to supply many, many images of bricks in the context of my conveyor belt. You can see one example image here if you look at the image on the right. You also need to label the individual bricks, which I can show that in a second, but it's a bit tedious, but it's made quite easy with the features available in Studio. With the images uploaded and labeled, I'll add an impulse in Edge Impulse Studio, which effectively represents the machine learning pipeline that I'm building. And the end result is a model that can spot individual bricks from video frames at a reasonably high rate. I was surprised at how well it worked even on the Raspberry Pi. So now that in theory I can identify bricks, I next want to identify anomalies in those bricks. So to do that, I need to capture a new set of very concise images of the bricks themselves and then load those into a new Edge Impulse Studio project to start building out this visual anomaly detection model. Again, I'll add an impulse to the project in Edge Impulse Studio. Building, training, testing the model, all is done within the web UI provided in Studio. I did include this image, which I thought was interesting. It's part of the testing process because it was fascinating for me to see from my testing results that this image was flagged as an anomaly. And it really reminded me that context is everything in ML. In this case, there is one small part of the conveyor belt here that reflects light much more brightly than the rest of the conveyor belt. And so when a brick was placed in that exact spot, the difference in light reflected was enough to trigger an anomaly. Just something to keep in mind as you're building out your more complicated models. So with the models created, we need supporting hardware. That starts with my Raspberry Pi 5. It looks kind of jacked up because I have a cooler on it, but I promise you it's just a stock Pi. Along with a new midband, LT Cat 1 Biz, note card, and a note carrier Pi hat to make it all easy to assemble. Again, this provides me that secure off the local IT network cloud access. Combine it all into one reasonably compact solution here. Also using the Pi Camera V2 module, I believe, all ready to process my bricks. That's not all. We haven't even touched on the cloud part. We're going to need to set up a new project in NoteHub. And NoteHub is free to get started with 5,000 free events per month. Again, NoteHub, like TJ mentioned, is that secure cloud proxy that pairs with the note card to sync our data, which today, if you squint a little bit, maybe you can see in the bottom right a count of anomalies I'll be sending in a given brick along with the base64 encoded binary image payload of the anomalous brick anomalous image as well. And then through NoteHub, we're going to directly integrate with AWS. In AWS, we'll simply be using a Lambda function with Python. This Lambda is going to accept two pieces of data from my note card events. One is the anomaly count. The second is that base64 encoded payload. We're going to save that payload as a JPEG in an S3 bucket. And then using the Twilio and SendGrid libraries, we're going to send a text message and email message with the alerts. Now, lastly, in the Python script running on the Pi, we're going to be using the NotePython library that TJ mentioned. We can take advantage of those easy JSON-based commands, which today are literally two commands here. The hub.set API is going to tell our note card where in NoteHub, where in the cloud the data should go. And then the note.add API is going to send anomalous data, detected anomalies in notes or in events to NoteHub. And specifically, again, we'll be sending these counts of anomalies found on each brick along with that base64 encoded binary image. And then to give away the end result, we're going to get a constant stream of bricks being analyzed. And then when anomalies are detected, we'll get these fantastic alerts via SMS and email. Again, I just threw a ton at you, but the individual pieces are surprisingly simple. And we will be supplying all the code used in a GitHub repo or through a Hackster project I created at the end. But I just wanted you to have this just in case anything goes wrong, but I'll be effectively repeating everything in what's really my demo right now. So let me shift.
What could possibly go wrong?
You wouldn't believe what could go wrong. All right, let's share my entire desktop. Get rid of my Zoom window. Does that look good? You seen things okay?
Yeah.
Okay, great. So again, the first step in my project was to create a new project in Edge Impulse Studio. So I wanted to create an object detection project, which again, I needed some way to detect the bricks that were coming down the conveyor belt. So, and the first step in building effectively any project, any model in Edge Impulse Studio is the data acquisition step. So you're going to need, in our case, supply images, but you might be supplying like accelerometer data, so XYZ position data. You might be supplying wave files if you have a sound-based project as well. In my case, we're just talking about images, right? And so I supplied 100 images that were taken from my Pi camera in context on the device itself. And I uploaded all of those images through the UI provided. One disclaimer, 100 images is not a lot for a project like this. It was enough for me to get started and you'll see it works, but in a real world scenario, I'd probably like 10x that, just to be safe. Another useful tidbit when using Edge Impulse Studio, it's going to automatically split your data into training sets and testing sets. We'll talk about the testing set in a little bit, but effectively what that's doing is saying, we're going to train your model on this 80%. We're not going to train it on that other 20%. We're going to allocate that to actually test the model after it's been created in the cloud. All right, so we'll show that off in a second. Again, the second step after acquiring data is going to be labeling individual items, objects in the images. And again, this process is a little bit tedious, right? Because for every image, you got to go through and say, yep, this is a brick, this is a brick, this is a brick. However, the studio effectively ends up learning what you're doing over time. And so as you advance to the next image, it will kind of pre-populate some bounding boxes for you. And I'd say probably 60-70% of the time it gets it right. So we can get through this, like, even for me to get through like 100 images wasn't too bad, right? I got through it in probably like a half hour or so. So not too terrible. Once I've got my images loaded in Studio, properly labeled, I'm going to create an impulse, which if you remember is effectively my ML pipeline. And this is where I get to say, like, I'm a total idiot. I don't know anything about machine learning or developing models. And the beauty of Edge Impulse is that it's going to elicit from the data I've already entered, the data I've already uploaded, it's going to give me some pretty good guesses about what I'm trying to do. So it's like, yeah, for the processing block, we're dealing with images, right? And then in the learning block, and I can't remember where this came up in the process, but it was when I started up the project. I think I was able to choose that this is an object detection project in the beginning. So it automatically suggested this learning block of object detection based on the images.
When you start collecting images, it'll prompt you for detection or classification.
Yeah, that was all I had to do. Once the impulse was saved, the next step was for me to generate features. I'm creating a pretty simple model here, right? Just one feature. I just want to know where the bricks are, right? So that's the one feature I needed to create. And yes, I'm glossing over a lot, but just want to give you a general sense of the workflow. Training the model, again, using the defaults provided by Studio. The result is this F1 score, which you guys can correct me if I'm wrong, but is effectively like a quality score of the model. Close enough.
Yeah. It's based upon the validation size that's set aside. I think it might be under your advanced training settings, but yeah, don't worry about it.
Yeah.
That's exactly
Yeah,
what it is.
the F1 score is
98.6.
kind of, it's a combination. Yeah,
Okay.
just like it
98.6 sounded pretty good to me. So, uh, with my model trained, again, like the important thing to know here is that I'm not training this. I don't need like a 4090 GPU running my desktop here. This is all done in the cloud. Like there's no local dependencies required at this point. And then I can advance onto the model testing, which again is all done in the cloud. So this is the labeled images that were set aside in our testing set. Hit one button that says classify them all, goes through, boom, 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 tests each one of them. 94% accuracy, pretty darn good. But what I find very interesting is that we can then drill in to see why certain objects were incorrectly labeled. And if I open up this classification, we can see more details. And sure enough, so I had labeled, there were 3 bricks in the image. I only labeled the back 2 because I actually didn't think the camera would spot that front one. But the opposite was true, right? It spotted the front 2 and not the back one. Using the tooling in Edge Impulse Studio, I can actually make corrections to my training set, or actually in my training and my testing set if I want to. I was certainly happy enough with the performance of this at this point. Now, let's say I'm happy with my model. It's time to deploy. Since I'm deploying to a Raspberry Pi, it's a Linux environment. I actually need to go in and install the Edge Impulse Linux CLI on my Pi. And then you run this Edge Impulse Linux runner command, which will let me download the model, literally downloads an EIM model file to the local file system. All right, that's the first project done. Now, at this point, I can do what? I can detect bricks on the conveyor belt. Next step, though, is I need to be able to um, look at those individual bricks and detect anomalies on those. So that's when I created this vision anomaly detection model here. So same first step as before, and that is to acquire images of, oh, interesting. Sorry, I got distracted by the, oh, is that you, Owen?
That's me. No,
Oh
that's
yeah.
me.
I'm like, how
That's
did
my
this show up?
camera's hooked up.
Yeah,
That's
no,
me.
that's great. So in this case, there is a feature in the Python script that I'll share later that will take cropped and zoomed images of individual bricks, and that's what I use to load up into the project here. And the nice thing about building up an anomaly detection model like this is I don't need to go and individually label objects because I know that they're all no anomaly, not anomalous. So you can effectively label them all when you upload them. And I'm just going to skip over some of these steps. Kind of the same thing as before. Use the defaults, generate features, train the
yeah,
model.
yeah, yeah. So we can
But
just maybe we can yeah. Sorry, we can maybe just take a quick look at the anomaly detection one there, just
sure.
on the anomaly detection section because you can switch. It's kind of important just to highlight here that we can switch between different types of visual anomaly detection core settings. So for larger devices like the Orin and the Pi, we're going to use patch core, which is a more complicated form of visual anomaly detection. It builds a kind of a base image that you're going to compare the new patches to, and that's where you get your score from. Whereas then you can, if you click on that patch score, you can swap that out for GMM for smaller devices, like if you were going to connect a camera up to the Swan or something like that. So microcontroller based. So I just wanted to show that just efficient. Just below that, you can see patch score. So you can actually swap out the just in your neural network architecture.
It looks like a button, Rob, towards the bottom.
Yeah, it looks like a button.
Oh my goodness.
So
Okay. Yes.
yeah, you can swap that out. So you can swap that out for GMM, which is like it's just going to
Oh, perfect.
use kind of like what we had for clustering, like clustering algorithm, and going to be able to compare it to get its anomaly score. Whereas the patch core is kind of a more advanced one where we really need to use things like Linux-based devices or GPU acceleration. But yeah, I just wanted to highlight that while we were going on through
No,
it,
that's great.
that we can swap that.
In the interest of time, I'm going to just fast forward here a little bit. So obviously we're going to go through the same steps to deploy this model to my Pi. Now let's take a look at the Python code a little bit here. This first Python script,
Bump
this
up
is the
your font
script.
size, Rob.
Oh yeah, sure.
Crank that.
This
That's
first
good.
Python script is what I use to actually generate this first set of images. So just backing up a little bit, just so you can see like all the images of the bricks going down the conveyor belt here. So not all that amazing here, right? We're just taking an image and we're cropping it down a little bit. The beauty here comes from this amazing project created by Edge Impulse's Louis Moreau. Did a great job on this project that I copied about 95% of his code to do this. Um, and let's
I copied more than that. I copied a full 100% when I deployed it.
I found there's a few highlights I want to make sure we hit here. And starting with, okay, so in this Python application, again, we need to initialize access to the note card, which again is just is done with the hub.set API. And that's going to be, it's going to effectively attach that note card to my Node Hub project, which I'll show in a second. This is an optional step. When using the note card, you can create templates, which are effectively hints that let the note card store and send data more efficiently. Again, optional. And whoops, this is getting ahead of myself. The first step of my model, remember, as the video feed is coming through the camera, it's going to look at every frame. I think it's like 30 frames per second. So it's running quite a few frames through this. It is going to actively identify and classify objects in real time. Now, if an object is identified, we are then going to draw some bounding boxes or draw some bounding boxes isn't quite the right term, but it's going to draw some UI elements on the screen. And I failed to mention that this is also a Flask-based project. So we're going to have a web UI that's going to show us a live stream of the video and anomalies that are detected. So this is just some nice fancy UI drawing on there. Now, once we found an object, we then need to pass that object, that cropped image of that object through the anomaly detection model. And if anomalies are detected in the image, we are going to send an alert. However, we're going to specify that only if we find 60 or more anomalies in the image. 60 may seem like a lot, but the model that we've developed gets pretty darn picky. And so I found 60 to be a good threshold for what a real anomalous image would look like. We also have this cooldown interval set. Basically, you don't want to spam your alerts, your SMS or email by sending, 30 SMS messages in 1 second. So we have like a 60-second cooldown to make sure that we're not overdoing it on the alerts. That's about it. I think the last part is here. If we are sending an alert, we're going to compress the JPEG down a little bit more. We want to get it down to a reasonable size to send it really quickly. And we're going to base64 encode that image. And then we're going to send a note, which remember is just an event in Blues parlance. And it's going to include the number of anomalies and then the string, the base64 encoded string of the image itself. And that data is going to go up into NodeHub. And here's just a look at my NodeHub instance. I've got a specific project for this demo here. And we can see my one device here. I can pump the size up a little bit just to see an example event. So here's one of my anomalous events. I can drill into the JSON so we can see here's that exact like anomaly data along with the image data as well. And I've got one route here. Again, this is the route to AWS. And I'm going really quickly here, but this is frankly as easy as it looks. To create a route in NodeHub for AWS, I'm going to use a Lambda. I'm pasting in the function URL provided by that Lambda, and I'm specifying only route anomaly.qo note files. That's what I determined is an anomalous data. I don't want to send any other extraneous events that may come through based on like the health of the device or any log files or anything. And that's really it. Let me hop over to, here's my Lambda function, which we'll share this at the end. Really quickly here, we're extracting the anomalies from the event and the base64 encoded string. We're going to decode that. We are going to upload that and save it as a JPEG in my S3 bucket. We're then going to generate a secure URL for that file that we just created in the S3 bucket. Again, it's just a few lines of code here. Once we've got all that information, I can use the Twilio, or sorry, the SendGrid, well, Twilio SendGrid now, API to send an anomaly and then, or send the anomaly notification and then attach that image as well. And lastly, we're going to send an SMS with the Twilio API. And we're going to attach the image as a media URL, as they call it. And just to pop over to my S3 bucket, you can see here's a bunch of the images that have gone through. And I always think it's interesting. The fairly decent quality image will come through. It's only 1.7 to 4 kilobytes, so really easy to send that really quickly over cellular. Now for the grand demonstration here, this is a feed into my Raspberry Pi. Let me start the application here. We're going to initialize the note cards. You're going to see a lot of debugging information over there. And we will see, here's the live feed. If I wave my hand in here, you should see that. I'm going to turn on the conveyor belt, which hopefully won't screw anything up. It's really loud for me, but apparently you all can't hear it. And I'm going to load an image in there. So you can see it's generating those inferences, and it's looking pretty good, right? We're not seeing any anomalous data. Let's send another brick down the pipe.
Yeah, it's not loud. So
it's not loud. Okay, good. You can see that it thought it spotted one anomaly. Be curious to see what the results were on that. But I actually created 2 anomalous bricks. One where I scratched off part of the logo, and one that has an actual literal defect. It broke my heart to do this, but I had to break up my brick there. We'll run these 2 through. Actually, now that
I was wondering where you were going to get defective bricks from.
We're going to, I realized since I just created an anomaly, I got to wait 60 seconds. So while we're waiting for that first one, let's jump over to my text message, which we see what happened here was it looks like, again, this is kind of the result of a not a very well created model where it's detecting a lot of background noise as anomalies. So that was sent at 10:50 my time. We'll see if this one goes through. So now I've got a real anomaly, and we'll send that one through. Drum roll, please. Oh, of course. This isn't going to work now. You got to be kidding me. I tested this
I don't know if it's been 60 seconds, but
yeah, I think it hasn't been 60 seconds.
I don't think it's been 60 seconds yet.
How many images was in that set, Rob? You said, was it 100 or?
100 images for both models, yeah.
Yes, 80 training and 20 test, because I just had a look at it. So it was really trained on 80, but it's a good talking point, Rob, actually. What you're experiencing there, I got when I ran it locally here as well, which is the backgrounds. At production scale, you need more than 80 images, and I don't have an exact number to provide you, but what you really need is diversity in backgrounds, diversity in lighting, diversity in the angle, the orientation of the object. You need to have a very robust data set. I actually just was doing some very, very quick testing just the other day on, I was using an apple and an orange, literally just whatever I had around to try to differentiate. And that was the biggest factor. Was I took all these pictures of an apple and I took all these pictures of an orange, but because I only had one background, the model could not differentiate between the two. So you really need a variety, a robust data set.
Mm-hmm. So that's a great point, because if you look at what the text message that was just sent, it caught my hand placing a brick.
Oh, look at that. Yep.
Again, of course that's anomalous, based on what the model knows. So I'm going to try one more here with, I'm
just sharing out we have an article as well in the docs just on improving your model. And particularly whenever we go to an event as well, you nearly have to retrain your model at the event, because different unanticipated scenarios, lighting, sound. So yeah, you're
And
Even if you
that,
had, yeah.
yeah,
But
and that
sorry, go on.
comes full circle. Well, that comes full circle to one of the talking points I had on my slide early, which may not have made total sense at the time, but now with this context, ML ops and collecting data from the field. When you go out into the field and deploy a model, deploy a device, what that camera on site sees is probably going to vary from the data set that you collected in the lab or in the office. And so you really need to go out there, deploy the device, and capture some images, or well, hopefully more than some, and bring that data set, those pictures, back into the studio and retrain the model. And that's how you then really improve your accuracy in that loop.
So we're very much low on time. I want to give Owen a
Yeah.
chance to chat too here. So
Yeah.
No, no, yeah. I wanted to just really highlight that we're able to optimize and scale up or down as well, so that, just to show you that we can swap out to different types of visual anomaly detection, like the GMM based one or the patch core, and that our models are natively run on the GPU as well. So if you run it on an Orin, it's going to be hardware accelerated by default. If you run it on a Pi, you're not going to get that kind of acceleration there. And it just gives you the scope to be able to scale your model up or down. And obviously, yeah, there we can see the Orin.
Yeah, I've
So
got
we've
one
just
on my
recently
desk.
added hardware support to run on the Orin. So it'll warm up your GPU, and then you can get even better accelerated inferences happening on your device. And I think if you want to learn more, are you guys are going to be at Embedded World as well this year, aren't you? I think,
yep,
yeah.
we'll be at Embedded World.
Yeah.
And
So
we'll
I
be
think,
there as well.
yeah, that was pretty much all I wanted to show there.
Okay,
And
great.
just kind of, if you want
Here, let me
to move on to the next.
yeah, I've just got uh, just want to share a recap slide here, and I will, just so everyone's aware, I will share that. Um, so everyone's aware well, obviously the three things I want you to know about this is how you access Edge Impulse Studio. Get a Blues starter kit at shop.blues.com. Most importantly, for the context of this webinar, I wrote up a project that I published on Hackster. It's available at this URL. From that project, you can get access to my GitHub repo as well that has all the code. But I'll also send out all this information in an email later on as well, along with the recording that we should get out tomorrow or Monday at the latest. So just make sure you had that. While we have a few minutes here, were there any questions that came up that anybody wanted to elaborate on publicly?
I think we handled most of them as they came in. Thanks everybody, because we had quite the active chat, so it was good to see that stuff coming in. I don't know if there's any I necessarily want to highlight, other than to mention that if we didn't get to your question for whatever reason, both of our respective forums are great places to follow up with that sort of thing, and we can help you out there.
Yeah, I see two quick ones that I'll grab over in the Q&A. First one was from Wolfgang, and he said the change from FOMO-AD to patch core, is that available to public free users or is that for enterprise? It's currently for enterprise, but I will say stay tuned because that might be changing in the near future. So Wolfgang, keep your eyes open on that one. And then there was a second one. Sylveon asked, is it possible to run more than one inference concurrently? I would say yes, because what you're actually doing in your demonstration that you just showed, Rob, was running more than one inference concurrently. You're basically using Python to bring two separate, like we talked about at the beginning, multi-model, or as we were discussing beforehand, multi-impulse, which is binarily down to one .eim model file execution. So yeah, it's possible to run more than one inference concurrently. And then I think this third one is a comment. Could it handle medical anomaly detection? Let's say a fractured hand. Well, yeah, in theory. Let's be clear, I'm not a doctor. So I'm only playing one on this webinar. But if you had a data set of, well, I guess, non-fractured hands.
Yeah, like a bunch of X-rays, right?
Yeah, a
Like if you
bunch of
trained it on X-ray
X-rays. You know, if
images,
you trained it
it
on
seems
X-rays
possible
and
that you could do it, but I
you
don't
know,
know.
a
Like,
hand is a hand is a hand. And then suddenly there's one that has a fracture through it. I could see how that would align sort of to the use case of like a crack in concrete or other surface material. So
Yeah.
I could see that being possible. Give it a test first.
I like there's
Yeah, I'll
a
bring the hammer.
Yeah.
I also like Howard asked a question. Philosophically, is running an Orin, especially if it's tethered, still considered an edge device? And I think that's pretty fun.
Yeah.
David, do you
I
want to
think
show that?
Well, you know, so the thing is so we
you're
were
doing the edge
talking.
inference, right? Yeah.
Yeah, you do the edge. The inference is running on the edge, and you know, with
Yeah.
a note card
Yeah.
on it, really all it needs at that point is power and the camera hooked up.
Hmm.
But remember that NVIDIA sells the Orin Nano developer kit, and that kit contains an SOM on a baseboard. But what they really are more interested in is productization of Orin SOMs. And so here is a good example of an industrial. This thing is steel. It's heavy. It would hurt if I hit you with it. And this is an AD-Link neon camera. There are, oops, I have that upside down, I suppose. There are other vendors as well. I know Advantech makes something more or less similar, but inside of this big steel chassis is an Orin Nano. So the same model will run accelerated on this as well. So the Orin Nano is good for prototyping, still on the desk. But really, when you go to production, you need something more enterprise grade, more industrial that will survive. You know, this one is intended, of course, for like a factory deployment. If you're talking about off-grid, you might be thinking more along the lines of like an NXP IMX8 ultra low power, or you might be thinking even an MCU world of you know, like a OpenMV cam, something that's an MCU that can run on battery power for a long time. So you kind of have to think about, well, what is the intended destination of the device? In a factory, just hook up Ethernet and power and you're good to go. This thing will survive, but it's not going to run on batteries out
Dave, as well.
field, you know. Yeah, go ahead.
Also in a factory, like we covered in our last session with the Opta here for the PLCs, you don't always have connectivity as well, and you don't want to be
Right, that's
sending data. So, like a factory could be as remote as a forest if you're trying to get a connection. So
Yeah,
that's a good
absolutely.
plug to the last session, I think, as well, if anyone's
Yep.
interested in more of the factory scenario.
Yeah, absolutely. And that's where Blues comes in to ease that connectivity burden in that factory. So yeah.
Why these webinars are so fun to do together.
Yes, they sure are.
Yeah.
All right, I think we're out of time. Thank you,
Yep.
all the speakers, very much. Thank you for everyone for attending, and yeah, we'll see you next time.